Hey, welcome back to Doc Onco's Physics Lessons. My name is Keith Onco. Today what we're going to be doing is taking a look at the magnetic forces and then the torques on a simple electric motor. Let me scroll down here just a little bit. What you see on the right hand side of the screen is the very basic parts of a simple electric motor. What we have are, oops, better switch that to pencil mode there. What we have are the magnetic field supplied by the north and the south end of a magnet, right? And if I draw in the magnetic field lines, they would look like this, right? I don't want to draw too many lines in there, or it gets a little bit difficult to see later. But so those red lines would be the magnetic field lines going from the north end to the south side of the magnet. Well, we also have in here, switch back to black, a current carrying wire. This blue wire here is a loop. It's a wire loop, and it's going to carry current, and the current is supplied by this battery on the lower part of the screen here. And then there's something called a commutator here, and it's basically a split ring so that it keeps the current going in the same direction as this wire loop spins. Okay, and you can see it's split in there, so it's not a continuous circuit in the circle here. But what happens is the current runs from the plus side of the battery. It runs through this wire here, all right, hits the commutator, and then goes through the blue wire loop along the right hand side here, up to the top, then down the left hand side, back to the commutator, and then back to the battery. So we have a current running through the wire loop. Well, we just finished a session as to what happens to a current carrying wire when it's in an external magnetic field. And we found out that there's a force on that wire. And the force, the equation for the force, I have over on the left hand side of the screen. And the magnetic force is equal to I, the current in the wire, times L, the portion of the wire that's in the magnetic field, times B, which is the strength of the external magnetic field. That would be the red lines here. All right, it's not the magnetic field created by the current carrying wire itself, it's the external magnetic field, times the sine of theta, right? And theta being the angle between the magnetic field and the current carrying wire. Now you'll notice, if you look at the direction here, along the right hand side we have the loop of wire that's in blue, all right, this section of wire in blue here, and I'm going to draw not an arrow here, but a line over here depicting which one I'm talking about. So it's the section of wire on the right hand side, and that is truly perpendicular to the magnetic field, as is the section of wire on the left hand side over here. It is also perpendicular to the magnetic field. But on the top, the section of wire that runs up here, that section of wire is parallel to the magnetic field. Okay, what's the angle for a line that's parallel to something else? Well, the angle is 0, and so the sine of 0 becomes 0. So the force on the top section of wire is going to be 0. There's not going to be a force in this depiction that we have here. All right, so that's one of the first things that we need to do, is figure out the forces that are on this wire that are in this external magnetic field. So the top wire doesn't have any. The right-hand wire, what we're going to have to do is we're going to have to use the good old right-hand rule, okay? And the right-hand rule that we're going to use is that my fingertips are going to point in the direction of the current. My palm is going to point in the direction of the magnetic field, and my thumb will point in the direction of the force on that section of wire. Okay, now we're assuming that this loop of wire, right, is held together by this commutator on the bottom, and it can spin. All right, so we're not just going to have forces on wire that's one's going to push up, one's going to push down, and it's not going to create something in chaos. All right, we're going to actually have something that can spin about a central axis, and that central axis would be the dashed line, right there. So the dashed line that I've drawn right there. Okay, so let's take a look at the wire, the section of wire on the right hand side. Right, so my fingertips are going to point in the direction of the current, and I'm going to be pointing at the direction of the current that's on my page. So you can do the same thing. Fingertips point in the direction of the current. Magnetic field is going to point in the, I'm going to have to do this with my hand now, all right? So fingertips pointing this way, magnetic field pointing to my right. And so the force on the section of right-hand wire is going to be going down. That's the direction that my thumb is pointing. So the force on this right-hand wire, I'm going to draw a big arrow here, is going to be going down. I'll call that FR. Okay, force on the right-hand section of wire. Well, by the same token, we can do the same thing with the section of wire that's on the left-hand side. My fingertips are going to point in that direction. My palm now is a little easier for me. It's going to point in the direction of the magnetic field, and my thumb is now pointing up. And you can see the force already drawn in here, that section of wire there. So the force on the section of the right-hand wire is pointing in the upward direction. Okay, so what's going to happen to this? Well, the force on the right-hand wire is pulling down. The force on the left-hand wire is pushing up. And this is rotating about some axis or pivot point. And so what we're going to have is we're going to have a torque on our motor, which is equal to the force, all right, or forces in this case, times the distance from the pivot point. Okay, so let's figure out what the forces are first. Well, we don't have any numbers yet, but let's assign some numbers. So let's say that the current in each section of wire, or the whole wire loop for that matter, is going to be 3 amps. And the magnetic field strength we're going to use is 0.05 Tesla, which is a pretty strong magnetic field. And the length of wire on each side is going to be 3 centimeters, or 0.03 meters. All right? And the distance from the dashed line in the center to each wire, and that would be this distance up here, right? So the distance from the dashed line to each section of wire is going to be 1 centimeter. So we're going to say R equals 1 centimeter or 0.01 meters. Okay, so let's first figure out the initial force on the current carrying wire. Well, let's see what we've got. We've got ILB, right? So the force is going to be equal to 3 amps times the length of wire, this loop of wire along the right-hand side or left-hand side, and that's 3 centimeters or 0.03 meters, times the magnetic field strength, 0.05 Tesla, right? And when we do that math on our calculator, what we come up with is 0.0045 newtons. Okay. So on each one of the sections of wire, I've got 0.0045 newtons. All right. And so the torque on the left-hand side of the wire, right, is going to be the force times the distance from the pivot point. So it's going to be 0.0045 newtons times the distance from the pivot point, which is going to be 1 centimeter or 0.01 meters. And so the torque on the left-hand side of the wire is 0.00045 Newton meters. Okay. Well, we've got 2 sections of wire, and the sum of the torques here, right? The sum of the torques is going to be the torque on the left-hand wire plus the torque on the right-hand wire. Well, the torque on the left-hand wire we've already found is 0.00045 Newton meters. Well, what's the torque on the right-hand section of wire going to be? Well, it's going to be the same thing because the force is the same and the distance from the pivot point is the same. Now, one question we have to ask ourselves is, what is the direction of rotation for the motor? Okay, are both of the torques going in a clockwise or counterclockwise direction? And they are, right? The left-hand section of wire is going to be pulling up, so that's going in a clockwise direction. The right-hand section of wire is pulling down, so that's going to be going in a clockwise direction. So they're both going to be, we'll consider clockwise to be positive, and we'll say that the sum of the torques then is going to be 0.00045 Newton meters from the left side plus 0.00045 newtons from Newton meters, I'm sorry, from the right side, And when we add all that up, we get 0.0009 Newton meters. And that would be the torque due to the interaction of magnetic fields, of the external magnetic field and the magnetic field created by the wires in our electric motor. Well, I hope that helps, and we will see you next time.